I know, like ice cream, right? Hello and welcome back to Calculus 2. Exam 3 review. I got confused with 2s and 3s and Calc 3 and Calc 2. I'm teaching both classes. I don't know. I did this in the morning for Calc 3. So, yes, welcome to Calculus 2 Exam 3 review. Perfect. The exam is on chapters 8 and 9. That's not 17. That's 8 and 9. So, chapters 8 and 9, sequences, series, and power series. So, those are the main topics. I just passed on me. Hold on. There we go. Sequences, series, power series. And we have these three. And as I said, it's going to be around, 10 problems. So 10 problems. Now, some might have A and B, and some, will be plain. Your job is to carefully read, obviously, and make sure you're answering the right stuff. Start from the. I just realized this. I didn't shut off the camera. Anyway. Off now. Huh? Off now. So 10 problems. Some might have A and B, and so on. We said that the most important part is to know the contents of that sheet, which I distributed in class, with a chart of all all series tests, all 10 of those. So what we have is sequences have only one test. That's it, one test. One test. And that one test is the limit test, which can go into convergence or divergence, and that's that. Series have 10 tests. And for power series, for convergence of power series, for interval convergence and radius of convergence, we generally use a ratio test, 99% of the time, and then a root test sneaks in, once in a while. So I'll just say 2 tests, ratio and root, but I'll put 99% over here and 1% over there, so there you go. Now watch me pick that one for the test. So that's the power series. So guys, how many tests do you actually have? You have 11 tests. 1 for sequence and 10 for series, and then the root and ratio series tests are used for power series as well. Sequence. Sequence is a list of ordered numbers. Series is the sum of the sequence. Power series is when you put in an x into a series. So it's very simple progression, right? It's like a number and then expression for a number and then a variable, which is a number and then adding numbers and then variables kick in, right, on top of that. So what are some of the rules that will save your life? Let's go orange. Rule 0 is learn the sheet. Because if you don't know the sheet, just skip. Stay home tomorrow, because there's really no reason for you to come in. That's rule 0. Number 1, try divergence test on your sheet known as nth term first, because that's the easiest test to use. It spots divergence. You're done with the problem. So if the limit of an is different than 0, it's divergent.
Does that also mean zero?
So if
That's also for infinity, right?
So if limit an is different than 0, it applies divergence, and you're done. Please make sure you never say it converges by divergence test, because that's just ridiculous. 2. So learn the sheet, try the divergence test. Then the next so no basic expansions. So you don't have to sit there forever to figure out the 3 basic expansions. So these are the ones that you should memorize. Guys, if you're taking differential equations, bite the bullet now, right? Don't wait till you get there, or partial differential equations later on and stuff like that. So e to the x is 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over. You don't have to go as far. You know, generally we like to use 3, 4, 5 terms. There is no reason to remember 17 per. Sine x is 1 minus x plus x cubed over 6 minus x to the 5 over 120. You know what? Let's not do 6 and this. Let's do 3 factorial and 5 factorial, and you can figure it out. So I'm going back to e. So 2 factorial, 3 factorial, 4 factorial. There you go. Cosine x is shame, holy nightmare. Sine is x minus x cubed over 3 factorial plus x to the holy nightmare. Cosine is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus forever. Oh, this one has, next one is minus 7 x to the 7 factorial. So all odd ones are in sine, all even ones are in cosine, which is why they're even and odd functions. Acute questions. Differentiate sine to, right, prove that the derivative of sine is cosine, prove that the derivative of cosine is negative sine, prove that the integral of cosine is sine, prove that the integral of sine is negative cosine. These are all cool questions that you can enjoy. So if I say prove that the integral of sine is cosine, well, integral of sine is negative cosine, well, if you don't know the expansion for sine, you will actually have to sit there for 30 minutes and figure it out, right? So knowing these, and they're so easy, because if you know e to the x is 1, and then x over 1 factorial, right, with the exponent of 1. So exponent of 1 divided by 1 factorial, we don't have to write them. Then 2, 2, 3, 3, 4, 4, all of them. What is the sine and cosine? Pick all the even ones, pick all the odd ones, right? That's what they are. Just pick them, and then you have alternation in signs. So you just have to do that. Now, those of you that are more vicious and you want to do even better in DFQs and stuff, cosine and sine hyperbolic. They are the other side of the coin of sine and cosine. Differential equations will have solutions either in sines or secant hyperbolics, depending on whether the sign in the equation is plus or minus, right? So you will have the solutions to be the waves or the squiggles, right? So these are the things that will greatly help you on the exam. You have learned the sheet, that's rule 0. Rule 1, try the divergence test first so you can knock out a few problems. 3, proofs for integral test. Now, if the problem says use integral test, well, in that case, the proofs are implied. If the problem says solve or test for convergence, and you think that the integral test is the one, you have to do all 3 proofs. So this is something that you have to be very careful, right? So if it says use the integral test, that means Well, obviously, since it's asking you to use the integral test, then it should be in the conditions, right, under conditions where you can use the integral test. When you're doing the integral test, guys, you have the limit with the improper integral and all that stuff. The integral in there is chapter 7, right? So it's either basic, or it's U sub, or it's trig sub, or it's trig sub followed by integration by parts and then casually turning into the by parts. I don't know. So I actually had a problem where you had to use 6 different techniques to solve it. It was really nicely constructed problems. So maybe I should make an exam for like chapter 7. Put that problem and one differential equation, and that's it. Right? That will be it. Well, we just followed, you know.
I mean, how many techniques did they get through before they quit, and then that's how many points you give them for it? It's great.
Yeah, but see, it would be really bad if you said, okay, I really don't want to learn the trig sub, and that's the first one. You see the problem, right? So everything that you skip because the system allows you to skip, eventually it is, which is the reason why I used to drop the highest grade rather than the lowest grade, which makes sense. If you have 10 quizzes, you drop the highest grade. Students are going to make sure they know everything, because every time they score 100, it's going to get dropped. Anytime you score 38, that counts, right? Where if you do it the other way around and you say, I'm going to drop the lowest grade, the student says, this stuff's too hard, I'm not going to do it, right? And then that one lecture kills the test, and kills the final, and then there's the next course coming up, and your education is over. And that's not exaggerating. I've seen that happen. I've seen that happen. I'm sorry to tell you, but you don't know now at this stage in the game what you need. You just have this idea of what's currently harder to grasp and what's easier to grasp. And then if you are not getting it, you are creating, right, aversion towards that particular topic, not knowing that that topic is going to be the basic building block for everything you do later, right? So, yeah. Anyway, so proof for integral test. Proofs for integral test, make sure you have all 3, right? Number 4, what else is important for the test? Make sure that you're alternating goes into AC or CC, right? That's the only one that has the...
What are the 3 interval tests? I think there's 2 things.
3 conditions. You have positive, decreasing, and continuous, right?
The decreasing, yeah.
Positive, decreasing, continuous. So you have three proofs to do. For alternating test is not the one that where you go converge, diverge. It is absolute convergence, conditional convergence. What else? Please don't use sequence to make arguments for convergence of a series. That doesn't work. Convergent sequence here. Do not generalize from sequences to series. Meaning, if you have an equals 1 over n, limit n goes to infinity of 1 over n equals 0, convergent sequence. If you have series 1 over n, divergent by p series, or integral test, whatever. See that? So you cannot look at the part of a series and say, oh yeah, that's a convergent sequence. Doesn't matter. There's the example right there, the most basic example that everyone needs to know. You need to know harmonic series. So there's the example right there. So do not generalize. That was one of my downfalls because I thought, you know, I can beat the system. You can't beat the system. You either know the sheet or go home. It's very simple. So that's that. Number 6. Let's put this one on. Geometric series start at 0. There we go. So if you have geometric series that starts at 2 to infinity for IRN, need to shift to 0, so S equals A over 1 minus R works. Otherwise it doesn't work. It's going to give you the garbage answer. So geometric series must start at 0. Number 7, telescoping. Watch for partial fraction decomposition. Because when you have a series of 1 over n minus 1, like this, that's telescoping. It doesn't look like telescoping, but as soon as you complete your partial fraction decomposition for this, it will be telescoping. Okay? So this will be telescoping series when you complete the partial fraction decomposition. So you have to watch for those things. There are a lot of little tricks and nasty stuff that can be hiding in these things. And primarily because you guys don't have enough experience with these things. This is type of mathematics you never dealt with before. This is street math, and yeah, I understand that it's all foreign and crazy and so on. Obviously, you'll do the best you can, but it's highly advisable to go back to these things and review all of this stuff, especially knowing that a whole chapter of DPQ depends on this. Yes.
For geometric series, if it diverges, do you need to worry about shifting?
No, because it adds to infinity, so we don't care. Any divergent series adds to infinity and we don't care, right? So if the geometric series converges and if it's not starting at 0, that's when you're doomed, right? You have to do the shift. After that, and then I have 2 examples on how to do shift. Yes?
Would this example just be like a list of numbers and like you have to figure out like
Good. You guys had some problems that I can look at, so you had a problem, right? Yeah, find the problem. Let me see what you guys have because they're already.
yeah,
The whole section. He asked if on the test there
Yeah, the example.
Oh, okay. I know.
All right, let's take a look. No, you're gonna take the notebook back. I just wanna. Oh, word. So, summation of k factorial squared over 2k factorial, like this.
N equals
1, 2. All right.
Oh yeah, that was on the phone.
Now, is this?
Hi, Mom.
Wait. Hi, Mom. Is the factorial? Can you just verify the factorial is in or out?
It's outside. Outside? Because that's the one that was, right?
Okay.
What difference does it make?
Huge difference.
If there's nothing inside, you probably won't be able to cancel stuff, and then you just be kind of like.
No, if it's on the inside, it's just 2k factorial. So it's just k factorial and then times 2. And this is just even numbers times 2. I mean, it's just even numbers. Yeah. All right, guys. Ready? We have the first problem to look at. This is series, and maybe this should actually make on our list of cool things. So let's just move this down and add another thing on the list. In orange, number 8, factorials equals ratio test. Ooh, I had no clue you can change the color like this. Look at that. They would definitely burn me on a stake for this like 400 years ago. Look at that. You can change the color like this on a glowing surface. Wow. Ratio test. Ratio test is going to take the limit of k plus 1 divided by ak. Should have switched this to n. We are looking for the number smaller than 1 for convergence or larger than 1 for divergence. If it's 1, it's inconclusive and you have to use something else. AK, in this case, is k factorial squared divided by 2k factorial. And AK plus 1 is k plus 1 factorial squared divided by 2k plus 1 factorial. So now I am going to skip a few steps over here by putting this and then times the flip of AK. You can also do some peeling. I have k plus 1 times k factorial, everything squared. So I peeled off k plus 1. And then divided by, on the bottom I have 2k plus 2, everything factorial, times 2k factorial divided by k factorial squared. So now time for algebra. Limit k goes to infinity. Now square will distribute over each factor. So we have k plus 1, that's going to be squared, and then I have k factorial squared, divided by, and now I have to peel two terms. I have to peel the term 2k plus 2, 2k plus 1, and that leaves me with 2k factorial times 2k factorial divided by k factorial squared. So these two die and these two die, and we are left with the limit k goes to infinity. And now what I have is, I don't actually need the absolute value anymore because all terms are positive. I have k plus 1 squared, which is of order k squared, divided by 2k plus 2 times 2k plus 1, which is of order 4k squared, if you get rid of everything else. So this is equal to 1/4, which is less than 1, which is convergent by ratio test. Bueno, huh? It's like magic. You want this on a test, you say?
Nah, so that's not right.
If it's on the test,
Yeah, this exact problem.
Yeah. I think I got it now.
Yeah.
But you make it like a factorial cubed over a factorial. I'm done.
So it'll just be like,
On par above the
that's the question.
You were asking me what's hard and what's easy. The whole thing is a joke, so I can't really tell you one from another. Every time you think that the professor wrote a disgustingly difficult exam because he hates you? No. It's just everything that we see over there is just a joke, and we can't pick hard from easy because everything is a joke. That's the thing. Now, clearly for you, you're going to have different opinion because there are concepts that are easier, concepts that are harder, right? So, right. Yes?
Okay, so I'm bad at algebra, and I don't get how you got the denominator in the second step up there.
You mean the, wait, second step, meaning this one?
Yeah.
Over here, we are taking out the terms. You have a plus 2,
Okay.
so that's the plus 2, and then the next one is plus 1, and then the next one is plus 0,
Oh, okay.
because you're counting 2, 1, 0, right?
Okay.
So we are taking just one term at a time. Yes? Behind, hold on. Can I scroll up a little bit? Sure. Is this good enough? You want more? So that's what the problem is. You have your AK, separately AK plus 1, and then we plug them in. And we do the peeling. Yeah. Well, most mistakes, like if I have to, I did in the past have the problems like this. Obviously, most of the mistakes happen here. You have to put k. You are replacing k by k plus 1, and then if you just put 2k plus 1, then you are missing this term, and then the whole thing diverges and gets the wrong answer. So you have to be careful with the.
What about like Taylor series stuff?
Yeah, Taylor series. Taylor, yes. All right, what do you have?
It says.
We'll get there.
It says use a comparison test or limit comparison test to determine whether or not the following series converges. And then it's between infinity and k equals 1, and then it's the square root of 16k to the 4th over 16k to the 6th plus 1. It's like the root stuff the whole thing.
16k to the 4th.
Over 16k to the 6th over plus 1. Or 16k plus 1, sorry.
Like this?
Yeah.
Nice.
Or like multiple choice.
Multiple choice?
Yeah, it says use the comparison test with 1 over k, or use the limit comparison test with 1 over k, and then just like converging it backwards.
Nice. So it diverges, obviously. I mean, that's obvious. See, this is what we talked about, right? It's obviously divergent series, right? And then so why, how, what?
Because 1 over k diverges.
Yes,
Yeah.
1 over k diverges. Done. Yes, that's you just solved the problem.
Yeah.
So now you go away. 1 over k. Yeah, 1 over k. Look, there's no plus 1, right? It's like when Neo bends the spoon. There's no spoon. Okay. So there's no plus 1. When there's no plus 1, 16 kills 16. Throw that in the garbage. So what you're left? You're left with square root of k to the 4 over k to the 6. That's 1 over k squared, and then the square root kills the square, you get 1 over k.
1. Oh, okay, that's what it is.
And 1 over k, right? So no, we'll do the problem in a detail, but
You got it. 1 over k.
well, I know, right?
Hey, it's just like it's like a Wizard of Oz when they like
how would we
open
answer
the
that?
curtain. It's just so
That's I'm gonna work out everything. So just you know.
Like in the answer, like say because 1 over k diverges.
yeah.
I'll put 1 over k.
If you just let me write it out, you'll have the answer.
The way
Or we can just stare at each other like this and then leave at 7:15.
will this be limit again?
Like the disappointing problem. It's like the Wizard of Oz when they like see the wizard, they open it. He's just like this little dude behind the curtain.
Exactly. So yeah.
So is it limit or direct comparison?
I'll do limit. It's just whatever. So we have our comparison now. So as I said, as Neo in Matrix would say, there's no spoon, right? So that dies. And then you have 16 kills 16, in which case you are left with the square root of k to the 4 over k to the 6, which is square root of 1 over k squared, which is 1 over k, and there's your bn. bk in this case, right? So you get rid of the stuff that is whatever over there. You just keep the the highest exponents. You might have also some garbage in the numerator, right? If you have any garbage in the numerator, you know what the best troll move is to put plus sine of k to the 7th. Now that thing you can flat out ignore, because what sine? Sine is bounded between -1 and 1. It's not going to impact your sum at all. It's going to converge or diverge regardless if that thing is there, right? So unless you have a cosine n pi which turns into alternating series, but under the square root, no, right? So if you have a sine and cosine and they're not the alternating sines and cosines, you can just ignore them because they're bounded from -1 to 1. They're just not going to do anything. So now we have our bk. We also know that summation of 1 over k, which is bk, diverges because it's harmonic series. You can say by p series. So now, what do we have? Well, we have to go back to our previous. We have our limit test. The k goes to infinity. And we divide our square root of 16k to the 4th over 16k to the 6 plus 1 by 1 over k. Right? The limit of this is obviously 1.
Okay.
It's like, is it obvious that the limit is 1? Or it's not obvious that the limit is 1? So, what is the limit here? So, we have the limit, k goes to infinity. And then what I'm going to do is I'm going to write this as a square root of 16k to the 4th divided by 16k to the 6 plus 1 times k. Now I'm going to stuff this k under the square root, and when I stuff it, it's going to become k squared. So what I'm getting at here is limit k goes to infinity, and then when I stuff this in, it's going to be 16k to the 4th times k squared, because it will be k over 1, divided by 16k to the 6 plus 1. This is the limit k goes to infinity, square root of 16k to the 6 over 16k to the 6 plus 1. Now we do the root of limit, right? We swap the spot of this because properties of limits in Calc 1 teaches that we can do that. So we swap those, and you just have to do the 16k to the 6 over 16k to the 6 plus 1, which is clearly square root of 1, which is 1. So we got that L is equal to 1. And now your answer comes in.
So just like plug in 1 over k for the
What?
So just plug in 1 over k for the whole message.
Yeah, so it's the whole 16. So it's just 1 over k divided by 1 over k, which is just 1.
No, you can't do that.
No?
No, you have to divide the original problem with your comparison. Because then every problem would be just divide bn with bn, and every problem would be 1.
Bn by breaking down what
Yeah.
it was.
No. You're dividing the problem with, we are dividing the problem with what it is.
You can't do some flat right now.
No.
Okay.
Answer. Bam. Since the limit of ak over bk is equal to 1, and summation bn or bk, whatever, diverges, series summation of your square roots and your 16s and stuff diverges by limit comparison. Bueno. Are you happy with the answer now?
Yeah.
All right. Any other questions, concerns?
on the tail shows like the Connor series ones where like
Okay.
it does do this stuff, not just like get the formula, but like do the radius and all that.
Yeah, give me the problem. There's a whole section on, right?
It's broken down into that.
Yeah, look for 9.2 homework exercises. They will say radius of convergence and interval of convergence.
Find the interval and radius.
Yes. So give me the power series. So find the interval and radius of convergence. And what do you have?
That's something like properties power series. Right? Would be that.
9.2, yeah.
That would be 17x to the k.
17
X, and then that whole thing to the k.
like this.
Yeah.
Okay. As a?
It's like column 4.
Okay. So it converges at 0, and that's it. And radius of convergence is 0. Done. Next. Because there's nothing here. It's... Oh no, I lied. It's power series. Okay. It's a geometric series, yes. So 0 to infinity or 1 to infinity? What does he have over there? Doesn't say anything, so 0 to infinity is easy. All right, guys. So this is a little bit of the oddball of the problem. We will do this with ratio test. It's the oddball of the problem because it's geometric. If you see, it's a geometric series. So I want to solve this first with geometric series, and then we'll go to the standard way. Okay, just because we can. So geometric series setup. Now, what we know for geometric series is converge if R is in between a -1 and +1. Your R is 17x, and that needs to be between -1 and 1. Divide both sides by 17. So -1 over 17 less than x less than 1 over 17. And that's the interval of convergence. So interval of convergence is from -1 over 17 to +1 over 17. It's centered at 0, and the radius is 1 over 17. So this is unconventional way of solving this, just because the entire problem is actually geometric series. It converges at 0, as I said, but 0 is in the right between -1 over 17 and +1 17. Now, our standard way to deal with this is to actually do the ratio test. So for ratio test, we have that our AK is 17x to the k, and our AK plus 1 is 17x to the k plus 1. So now we are going to do the limit as k goes to infinity. Absolute value is absolutely important. We have 17x times 17x to the k, that's when we peel 1, divided by 17x to the k, which is the AK. Now these two will drop, and we are dealing with the limit of absolute value of 17k. Now that is equal to 17, absolute value of 17k, and we set that equal to 1. So again, we didn't have to do the limit because, not k, x's. What the hell am I talking about? 17x and 17x. The variable on which limit operates is k. There are no k's in this limit. Therefore, whatever the argument of the limit is the answer for the limit. So now we have to deal with absolute 17x less than 1. If you know your algebra, you know that you need to put that in between -1 and +1, which is already this step here. And then we pick up from there -1 over 17 less than x less than 1 over 17. So that's the interval of convergence, and then r equals to 1 over 17, which is a half, is the radius. Of convergence. Happy?
Why was it after the something x less than 1?
Well, you are looking for interval of convergence, and by ratio test, you get your convergence when whatever the answer is smaller than 1. So you set this equal than less than 1.
Oh, okay.
Right? You won't convert. Let me just see. We set this less than 1 because we want convergence. This is the same like when you're dealing the derivative, right? To look for min and max, you set it equal to 0 to find critical points, because critical points occur when derivative is equal to 0 or when it doesn't exist. So you set it equal to 0 and then you go from there.
So this is the type of problem we'll get for
It's a typical problem.
power
Yes.
series. So wait, so power series will be broken down into like
Figure out the power. Yes.
finding the power series and then doing something like this.
Radius or convergence. Yes.
And then for sequences, is that the same thing? So like either just taking the limit of it or figuring out the sequence.
Yes.
But and then for and like backing up for alternating series.
Okay.
Alternating series wouldn't converge.
No, they can diverge if it equals 1 equals 0.
Yeah, wouldn't you be able to see that before you
Or if 1 doesn't equal 0.
Yes, you would see that. Very good.
Yeah.
You would see that before you in that limit.
And then if they diverge again, it's convergence.
So you have 3 choices there.
Oh, so wait, so the question was, when you get to this step, like when you get rid of the part that alternates it,
You get rid of immediately. Immediately.
Oh, so you take it out of the problem as soon as you see it.
Yeah, because the first thing is you only testing AN. That's the first part.
Oh, so
if it's decreasing, is it limit 0?
if it's cosine like n pi or whatever, like
You
whatever
take it out.
You take it out like you don't do any math to it at all. You just see it, you take it away, and then you.
Yeah, the negative 1 to the n term is never used in any of the calculations for alternating.
So the only test you really have to do is the a to n plus, or a n plus 1 is less than or equal to a n. You prove that.
If it's decreasing, yeah.
Or non equal. So you're gonna have to make us worry about non increasing. Okay. It's like every single problem is whatever. It's not that wrong. And then we just take the limit of it, I guess. Oh.
Making sure it's not 0, because if it's not 0, then we divert it by
Yeah, that's right. And then are we gonna have to worry about remainders for
yes.
doing the series? Well, no, I mean I don't mean that. I mean I understand power series, like for doing.
We talked about the remainder, and I said that all of your error, not all, most of your error.
No, I mean like for regular series. It's like 2 of these things have remainder.
Oh, it's the same thing. Yeah.
Okay.
It's the same thing. It's just the next term and then remainder. Yeah. Well, you don't have to worry about it, but it's the same basically. You don't have to worry about it.
On the test, we're not going to solve for remainder. We're just going to no.
For power series, yeah, but not for the.
Okay.
Power series are important because that's the error you're making in approximating a function. You
So can we do? Okay, I'll have to find one.
Yes.
Is there going to be a question where you give us a function and then you come up with a power series that you can see?
Yeah, that's the whole thing.
Okay.
That's the most important part of everything. Whatever function is given to you, I ask you to memorize e to the x sine and cosine for your convenience, but expand sine x to the 7th power, right? So you can do expansion there, or
You just like plug in next to the 7th is x, right? Okay, yeah. Or you plug in like whatever it is into x to the 1.
So sine of
You just be you square it, then or no, you cube it, then you x to the 5th, and then
yeah. So expand sine of ln x. That's the expansion without expansion, right?
Yeah.
Yes.
But I have this problem where it's the f of x equals 1 over 1 minus x cubed, because on the power series representation of 0, and the answer is just it has its own instead of
That means you can compress it. It's a polynomial that you can easily compress into something that looks different, right? So you can here. So if you take a look, so the question is, what do you do with the answers that they told you expand, but they give you a power series as the answer? So I asked you earlier to memorize e to the x as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... going forever. E to the x will be represented as a power series, and now you look at the pattern over here, you're coming up as x to the k divided by the k factorial, where k starts at 0 and goes to infinity. So I can memorize this law or this much. So it depends on which is the better thing for you to remember. Same thing goes for sine and cosine. Let's go cosine, for instance. Cosine x expansion was given as 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus ... forever. Well, cosine x can be also compressed into a series, right, where you start with 0 and go to infinity, of x raised to the 2n power divided by 2n factorial. So, and then you also have negative 1, because you have alternating signs, negative 1 raised to the n. So if you take a look now, this power series is actually compressed for this. Now, you are going to do that a lot, obviously, in your differential equations class, because you will solve the problem, get the recursion equation, and after an hour, right, you will have something like this. And when you get something like this, you will be compressing it into this, which will in fact tell you the function that is the solution to the differential equation. So this skill will be much more important as you go on in math. Right now, yeah, you compress it into this. So when you see an answer, don't let that confuse you, because if you expand that answer, you will get the expansion that you were expecting to see. Now, not every single answer will be possible to compress nicely like this, but for vast majority of them that you deal in calculus and DFQ, you will be able to compress, because we're careful on what we give. Yes?
So the remainder would come from if they want us to compute the value for like cosine of x.
Yeah, so cosine of 0.6.
Cosine of 0.6, you plug in 0.6 up until like say the sixth one, and the remainder is...
Yeah.
The remainder is the next term, but it's plugged in.
Yes, next term.
Right. And then
so in this case, your remainder will be calculated in x to the 8.
Or yeah.
Every even one. So x to the 8 over 8 factorial. Will be a very tiny number.
Yeah. So yeah, we just plug in the value of x in this. Right?
Yes. Now, when you're doing research and doing these things in the company environment, right? You know what kind of sensitivity, what kind of tolerance your device or whatever you're doing has to have. So you start from there, and you keep guessing which term is the one, right? So you know that would be the last term to have in your extension to have enough precision in your calculation. So you just do that one, and then if you want to be extra careful, you take one more. But you don't really want to drag 15 terms, right? So the tolerances and these things tell you how many terms you actually have. So you work backwards when it's money making time. That is it. Anything else?
For these in general, just like the derivative times x minus centering and
Divided by the k squared n factorial.
no.
That's the formula for Taylor series. I mean, you have to know.
Yeah, it's times the right
What would
side.
like the volume for Taylor series be though? Okay.
You gotta look at this.
Oh, that's right. You're all the same. Okay. Yeah,
Yes.
Never mind.
So would we get like maybe like did we get like a plan of x or whatever? Would that be like